migration rates of the solute. Okay, the chromatography is used to separate the mixture into the different components. So inside the chromatography, we have the mobile phase and we have the stationary phase. The mobile phase yang bergerak, while the stationary phase, the phase that is kept still ataupun tak bergerak. Okay, so in order for the separation to occur, there must be interaction between our analyte with the mobile phase and the stationary phase. Okay, kalau our analyte, kalau our component inside this mixture is more attracted to the stationary phase, so it will elute a little bit later. And then kalau kita punya component inside the mixture is attracted to the mobile phase, so it will eluted faster. Okay, so it will eluted faster and and form this big. Then after that barulah yang kuning, komponen kuning ni pula yang being eluted. Okay, so this peak we call it as chromatogram. Okay, so for the distribution constant, an analyte is in equilibrium between two phases, the mobile phase and the stationary phase. Okay, for the equilibrium constant ataupun K ataupun partition constant, okay, it can be calculated by the molar concentration of the analyte in the stationary phase divided by the molar concentration of the analyte in the mobile phase. Okay, then second one is the retention factor, which is represented by the K prime, or also known as capacity factor, is used to describe the migration rate of an analyte on a column. Okay, so the formula is the retention time minus by that time divided by the that time. Okay, so if the retention factor is less than or equal to 1, the separation is poor. If the retention factor is more than 30, then the separation is slow. Okay, so the optimum separation occur when the retention factor is between 2 to 10. Okay, so from the formula just now, okay, what is the retention time? Okay, retention time ataupun TR is the time for the analyte to pass through the column of the time between the sample injection and the analyte peak reaching a detector at the end of the column. So the time daripada dia start being injected, time 0 until dia go through the column and being eluted and form this peak. Okay, so this is the retention time for the component. Okay, the date time tu adalah the time a non-retained compound spends in the mobile phase. Okay, non-retained compound ni adalah kita punya mobile phase lah, bukan kita punya analyte. Okay, time required for an average molecule of mobile phase to pass through the column. So sebab tu that time tu dekat awal-awal you punya plot tu. Okay, so adjusted retention time or TR prime. Okay, you got this value by subtracting the dead time from the retention time. Okay, the selectivity factor adalah ratio capacity factor of two peak, and this describe the separation between the two component. Contohnya component A dan component B. Okay, selectivity ni is always greater than 1. Okay, if the selectivity equal to 1, the compound cannot be separated. Okay, the higher the selectivity, the more separation between two compounds are big. Okay, so the formula for selectivity is the capacity factor of peak B divided by capacity factor for peak A. And in this case, the species A or component A elute faster than species B. Okay, kalau dia bagi chromatogram, okay, this one is A, this one is B. Kenapa? Sebab A ini elute faster. Okay, description of column efficiency. Okay, macam mana kita nak tahu keberkesanan kolom tu? Okay, the efficiency is related to the number of compound that can be separated by the column. So the higher the number of compound ataupun the number of component that can be separated by the column, the higher the efficiency of the column. Okay, the efficiency ni boleh dipengaruhi of the theoretical plate which is represented by N, or can be influenced by the height equivalent to the theoretical plate. Okay, the efficiency increase as the height of the theoretical plate decrease. Thus, more compound can be separated by the column and vice versa. Okay, so what is the theoretical? Okay, what is the theoretical plate model of chromatography? Okay, actually the plate model ni adalah model which propose that the chromatographic column contains a large number of separate layer. Okay, so the analyte move down the column by transfer of equilibrated mobile phase from one plate to the next. Okay, this one is the theoretical plate rule. Okay, setiap satu ni adalah different theoretical plate, and then the height of this plate is represented by H ataupun HATP tadi. Okay, so untuk every plate ni dia akan berlaku transfer of the mobile phase from one plate to the next. So untuk setiap plate ni akan berlaku separation. Okay. So note that the plates do not really exist. They are just figment of imagination in order to understand the separation process in the column. So actually this theoretical plate inside the column ni tak wujud pun, kita tak ada tengok dalam mata kasar pun, tapi it is done theoretically in order to understand the separation process in the column. Okay, at each plate ni dia nak pergi ke plate lain akan berlaku separation. Why? Because transfer of equilibrated mobile phase from one plate to the next. Okay, the height of the plate can be calculated by dividing the length of the column by the number of theoretical plate. Okay, so from the chromatogram ataupun bila kita tengok the peak that muncul due to the chromatography, we can calculate the theoretical plate. How? By using these two formula. Okay, so untuk kira theoretical plate, kita boleh divide 16 darab dengan retention time bahagi dengan width of the peak. Okay, retention time ni time daripada sini. Okay, sini time, sini adalah response. Retention time ni, okay, time daripada sini ke sini, and then bahagi dengan width of the peak. Okay, so boleh guna formula ni ataupun formula ni. Okay, so formula ni sama sahaja, beza dia width of the peak ni adalah half, peak width at half height. Okay, so kita kena kira the height of the peak and then kita bahagi 2. Column resolution. Okay, actually what is the resolution? Okay, the resolution is how well species have been separated. Okay, how well the component inside the mixture have been separated. So the formula for resolution is this. Okay, the retention time for B. Okay, B, this one, the second peak. Then the retention time for A. And then divide by width of A plus width of B. Okay, so you tengok kat sini je. Okay, and then acceptable resolution is equal to 1.0, and the best resolution between two peak require resolution more than 1.5. Okay, so untuk relatekan number of plate dengan selectivity factor dan juga retention factors, okay, we can use this equation, and if it is simplified, we can say that the resolution is equal to square root of the n. N is the number of theoretical plate. Okay, so the resolution values of less than 1 are considered unresolved peak. Okay, macam mana unresolved peak? Macam ni lah. Dia tak well separated. Okay, dia ni hampir nak well separated but not. Okay, so kalau RS dia adalah 1.5 dan the peak is well separated. Okay, the effect of resolution on the retention time. Okay, so we can use this equation to find the relationship, or if it is simplified, we can say that the retention time is equal to resolution square. Okay, so these are the questions. Okay, for the column resolution, just take the formula, then the average number of plate, the average plate height. So you can dapatkan daripada formula lah, cuma yang nombor 4 je yang complicated sikit. Length of column to achieve resolution 1.5. Okay. Oh, okay, dia keluar macam ni. Okay, so basically 1, 2, 3 you boleh buat. Okay, you try tengok. Okay, untuk yang nombor 4, dia tanya resolution yang kita dapat adalah 1.06. So dia tanya, kalau 1.5, kalau kita dapatkan resolution 1.5, berapa kita punya length of column. So you try buat equation macam ni. You samakan, then you akan dapat n. Value of n, lepas tu you masukkan dalam formula ni. Okay, try to understand this. Variables affecting column efficiency. Okay, there are 4 variables that can affect the column efficiency. Okay, but first remember, the efficiency of the column depends on the number of the components that can be separated by the column, and it is also depends on the h. H is the height of the theoretical plate, and the n number of the theoretical plate. Okay, the lower the height of the theoretical plate, the higher the efficiency. The higher of the number of theoretical plate, the higher the efficiency. Okay, first of all, we see the effect of the mobile phase flow rate. Okay, mobile phase flow rate inside the column. Okay, from both the plot for liquid chromatography and gas chromatography, we can see that the graph is the height of the theoretical plate over the flow against the flow rate. Okay, we can see that both show a minimum in H, okay, dekat sini, at low flow rate. So we can say that H, the height of the plate, increase as the mobile phase flow rate increase. So in terms of efficiency, it will decrease the efficiencies. Kenapa? Sebab the lower the H, the higher the efficiency. So kalau H increase, the efficiency will decrease. So in this case, the mobile phase flow rate kena decrease, barulah efficiency ni akan increase. Okay, so the second one is the effect of the particle size. The effect of the particle size of the packing material or the stationary phase. Okay, the numbers to the right is the packing particle diameters. Okay, ni diameter of the packing material lah. Okay, yang bawah ni yang paling kecil sekali. Okay, so kita kata the smaller the particle size, the more pressure is needed to push the mobile phase through the column. So H increase as the particle size increase, and then this will decrease the efficiency. So untuk dapatkan high efficiency of the column, the particle size must decrease lah, must be small. Okay, the third one, the effect of the diameter of the column. Okay, for packed column, the most important variable that affect column efficiency is the diameter of the particle that making up the packing. The increase the diameter of the packing material has stationary phase. The increase in column diameter will increase the plate height. So this will decrease the efficiency kalau diameter dia adalah increase. So untuk dapatkan high efficiency, the column diameter must be decreased. Okay, then the last one is the film thickness. Okay, film thickness ni adalah the film thickness of the stationary phase. Okay, with thick film yang tebal makes the analyte molecule travel slower. As a result, thick film will increase in plate height, and this will decrease the efficiency. Why? Because the plate height is increased. So untuk dapatkan high efficiency, the film tu kenalah thin film. Application of chromatography. Okay, for qualitative and quantitative analysis. Okay, for the qualitative, we can compare the retention time of this, let's say of this peak. We can compare with the standard in order to get the qualitative analysis. We want to know what this peak represent which component. Okay, this one is for qualitative. Kita nak tahu peak yang keluar tu at retention time berapa-berapa is equal to which component apa. And then for the quantitative, okay, based on the peak area and or the peak height will tell us how much of compound is there, the concentration of the compound. Okay, for qualitative analysis based on the retention time. Okay, the sample provided produced the peak at the same retention time as a standard under identical condition. Okay, this one macam you buat HPLC hari tu, you nak cari dalam soft drink tu ada tak peak caffeine. So, you prepare the standard caffeine and also the Pepsi, the Cola, the 100 plus soft drink. Okay, so mula-mula you run the caffeine. So, you tahu caffeine you tu dekat berapa? Dekat, contoh kata dekat 4 minit ke 4 lah kan. So, dalam sampel Pepsi you, kalau you tengok peak yang keluar minit yang 4, yang tu adalah caffeine lah. Okay, so kita boleh determine the presence of caffeine inside the Pepsi. Sama juga dengan Coke, sama dekat dengan 100 plus. Ada tak peak yang sama dengan caffeine peak dengan dekat standard ni? Okay, so macam tu. Okay, this one also the same. Chromatogram of the standard sample, aspartame. Aspartame ni adalah sweetener, artificial sweetener. So, kita pun run dulu standard sample dan kita dapati aspartame ni ada dekat minit ke contoh 13 lah kan. Okay. So, kita pun run pula the beverage. Okay, soft drink apa-apa. So, kita pun tengok ada peak yang muncul dekat 13. So, kita boleh kata peak ni adalah peak aspartame. Okay, so untuk tahu dia punya how much aspartame is present inside this beverage, inside this soft drink, we have to calculate quantitatively lah, ikut this formula yang kita akan tengok later. Okay. Okay, for the quantitative analysis, the first one is based on the peak height. Okay, so kita boleh kira the height of the peak by connecting the baseline on either side of the peak by a straight line and measuring the perpendicular distance. Okay, so macam mana nak tahu? Kita boleh kira melalui height of the peak. So, kita kena buat baseline dulu. You straight lah kan? Ni tangan saya tak straight. Okay. Okay, so you boleh kira the height of the peak. Okay, tadi macam mana nak kira the peak height. So, sekarang macam mana nak kira the peak area. Actually, the peak area and the peak height yang kita belajar tadi adalah untuk dimasukkan dalam equation of the concentration. Okay, so untuk kira peak area, you boleh guna formula ni. The height of the peak ni, the height of the peak ni darab dengan the width at half height. Okay, half height and ni sini bahagi 2, contohnya kat sini. Kan, bahagi 2. So, the width kat sini. So, darab 2 ni, you akan dapat the area of the peak. Okay, so langkah ketiga, cara ketiga kita boleh juga nak tahu the amount of that component inside. Contohnya, nak tahu the amount of aspartame dalam the beverage tadi, kita boleh guna the calibration method ataupun external method. Macam mana? Okay, by preparing a series of standard solution yang kita tahu composition dia. kita tahu concentration dia. Contoh kata aspartame tadi kita buat kita dilute 5 microgram per lead, 10, 15, 20, 25. So kita pun masukkan dalam chromatography, kita pun kira peak area dia berapa. Okay, so at the same time kita masukkan unknown kita. So unknown kita tu kita tak tahu berapa concentration dia. Tapi bila kita masukkan dalam chromatography apa-apa, kita akan dapatkan peak unknown kita. So peak unknown kita tu kita pun kira peak area, and kita pun boleh macam ni, dan kita boleh tahu okay, kita punya unknown aspartame dalam beverage tadi adalah about at 13 microgram per liter. So macam ni. So calibration method ni, okay, you dah pernah belajar lah sebelum ni. Calibration method ni adalah by preparing a series of standard solution and we compare macam ni. Okay, untuk internal standard method, dia adalah opposite dengan external standard method tadi. So kalau internal standard method, okay, dalam kita punya sampel tu kita akan add standard. Okay, so kalau dalam external tadi, kita punya sampel lah standard lah kan. Okay, so kali ni untuk every sample kita tu kita tambahkan standard at different concentration. So you boleh baca kenapa. And then, okay, so the plot is the area ratio, this one, versus concentration of the analyte in standard solution. Okay, so nanti kita boleh extrapolate macam ni lah. Okay, dan dapat concentration of analyte. Okay, signal from analyte is compared with signal from the internal standard to find out how much analyte is present. Okay, analysis based on peak area using response factor method. Okay, the formula for response factor method is peak area of unknown compound X bahagi dengan concentration of compound X. Okay, so ni adalah response factor untuk kita punya unknown. Okay, response factor untuk kita punya standard pun kita tahu, in which the peak area of the standard bahagi dengan concentration of the standard. So dua-dua ni kita tahu concentration of the standard. So in order to get the concentration of compound X ataupun unknown, kita boleh compare between these two response factor. Okay, untuk lagi faham, kita akan tengok the next example. Then lagi kita tengok this example. An injection containing benzene at the concentration of 2000 microgram per mil is made and result in a peak area of 100,000. Okay, ni concentration ni adalah peak area of the benzene. Okay, benzene ni yang kita tahulah. Lepas tu an injection ataupun standard. Okay, an injection of sample with the unknown concentration of benzene. Okay, ni sample with unknown concentration of benzene ni sample kita lah, analyte. Has a peak area of 57,000. Calculate the concentration of benzene present in the sample. Okay, macam mana yang nak buat? First of all, you kena kena tahu the response factor for benzene. Macam mana tadi? Nak kira kita peak area bahagi dengan concentration. Dapatlah 50 dia punya response factor. And then nak tahu concentration of benzene in the sample, kita pun kira sebab kita dah tahu response factor. So macam mana nak kira concentration of benzene, kita bahagikan peak area bahagi dengan response factor, dan kita akan dapat the concentration of benzene in a sample. So kita ikut formula tadilah. Okay, in which the response factor equal to peak area over the concentration. Okay, untuk area normalization method ni kita guna this formula. Okay, the percentage content of one or more component of the substance to be examined is calculated by determining the area of the peak as a percentage of the total area of all the peak. Okay, ni exclude solvent dan any added reagent. So, okay, the content of the component in the sample C concentration equal to AI ni adalah area of component peak in the chromatogram over total area of the peak in the chromatogram. Okay, so nak faham, kita tengok this example lah. Okay, a mixture containing only 3 compound X, Y, Z. Okay, dalam you punya sampel, dia ada mixture tu ada 3 compound X, Y dan Z. An injection of 1 microliter of the mixture resulted a chromatogram with peak areas of 232, 650 and 984 arbitrary unit. Calculate the percentage of each compound. Okay, macam mana? Okay, ni adalah dia punya peak area. So, peak area dia untuk X ni adalah 232. Lepas tu, you divide by 1866 ni adalah hasil tambah peak area, total peak area for X, Y dan Z. 232 campur 650 campur 984. Okay, so you pun darat 100. So, you pun tahulah peak X ni, dia punya persen dia adalah 12.43%. Okay, so you pun boleh kira for each composition how many percent is there inside the sample. How? By dividing the peak area with the peak area of that compound divide by the total area. Okay, dalam kita punya chromatogram ataupun peak, okay, mungkin akan berlaku tailing. Okay, this one is tailing and fronting. This one fronting. Dia deviate daripada ideal shape. Okay, kalau fronting ni dia jadi separuh macam ni. Kalau tailing dia jadi terlebih macam ni. Okay, this happen due to the distribution constant that varies with the concentration. And also fronting ni juga berlaku due to the introduce of the high amount of sample is introduced into the column. Okay, so how about the band broadening? Okay, band broadening ni bila peak kita dia jadi broad macam ni. Okay, so bila peak kita broad dia akan affect the efficiency. Okay, why it affect the efficiency? Sebabnya okay, the higher atau the broader the band, the smaller the number of component that can be separated. So this will cause the decrease in efficiency. Okay, so these are the factor that can reduce the band broadening.